Here are the solutions to homework set number 11 for ECE 463 Modern Control. The first problem is looking at a cart and pendulum system. So what I'm trying to do is control a cart and pendulum system, kind of like this system, have it go from point A to point B, track a constant set point, when I only measure position and angle. So how do I do that? Well, I'll start with the dynamics. Here's the linearized dynamics of the cart and pendulum system. I've got noise at the input, this mean of 0, standard deviation 0.2. I can measure position. It's got noise on it, standard deviation 0.05, and angle, standard deviation 0.01. The first step is come up with a control law. Here I'm using a servo compensator. So create the augmented system, the plant, plus an integrator. That's my servo. I'm going to be integrating the position, because I want to track position. The input related to F, and I've got a couple inputs. So here my B matrix is actually a 5x2 matrix. So 4 states, 1 for the servo, actually 5x4 matrix. The first input is my set point, feeds the servo. The second input is the noise or input disturbance, feeds the plant through B. This is the noise on X. That feeds straight into the servo. And the noise on Q, which I'm not using. So given your system, form the augmented system, find your feedback gains using whatever method you want. I chose LQR, since that's the section we're working on, with the servo states. And if there's no noise, I use the step 3 function. Here's the closed loop A matrix, B matrix, C and D, time, initial value of 0, and my inputs. I've got my step input with no noise. If I do that, everything looks good. I'm tracking constant set point, have my settling time of about 10-ish seconds, less than 10% overshoot. Okay, so that looks good. If I add in the noise, here's the step response. Again, this is kind of cheating. I'm using all the states, even the ones I can't measure. But again, that's the separation principle, how you design the feedback control law and the observer are independent. Next, let's find the observer. The plant, well, if I use a full order observer, I place the observer poles someplace like -3, 4, 5, and 6. I get my observer gain H. This is the feedback gain for using the position measurement. I'm not using angle because pole placement doesn't really work when I have 2 inputs. So here's my closed loop system with the plant, servo, state estimator. H is actually HX and HQ, where the Q matrix is 0, 0, 0. I'm not using that one. That's your HC. The feedback gain times KX, where the noise comes in, is through the B matrix. If I simulate this system, form the closed loop system, my ninth order augmented system, plant plus observer plus servo compensator, my B matrix. Here's the B matrix with respect to the set point, with respect to the noise on the input, with respect to the noise on position measurement, noise on angle. I'm not using angle, so it's all 0. Plot the step response without noise. It looks just the same as before. That's what you expect. The observer tracks the plant states. If I start with no error, it stays at no error. If I do have noise, then in this case I change the D matrix. So here the pink line is the position plus noise on X, or the measurement Y sub X. So anyway, this guy right here is my measurement. That's the position. The clean line is my estimated output, or the observer estimate. And kind of see here, this is one of the reasons you might want to use the observer state rather than the actual measurement, because the observer helps filter out the noise. In addition, you kind of notice that there's a lot of noise on the output. Well, that's because the observer I chose is not optimal. It's just placing the poles. I can do better. Well, that's problem 3. Doing better is using a very specific observer called a Kalman filter. To find the observer gains, I use LQR techniques, where Q is the input, in this case it's just B, F transpose or FF transpose, times the variance of the noise, or standard deviation squared. R is a diagonal matrix, the variance on the noise on X, variance of the noise on angle. Find H, and what I wind up with are the optimal feedback gains. So this is the weighting on X, weighting on angle. The angle noise is 5 times smaller, squared, 5 squared times smaller. So I'm going to put a lot more emphasis on angle. And essentially, angle updates the second and fourth state, that's theta and theta dot, a little bit on the rest. And X primarily updates position and angle, or position and velocity. But they'll contribute. The first column is the H times X, second column H times Q. Where I put the observer poles, that's just wherever they wind up, that's the optimal place to put them. Form the augmented system, the ninth order system, plant plus servo plus observer, using the observer gains. Take the step response without noise. Looks just the same. With noise, however, you can see that the estimated output versus the measured output, that's your X plus noise on X, is much, much cleaner. That's the best you can do in terms of the smallest variance. That's the optimal observer, also known as a Kalman filter. And for comparison, if I make the set point 0, it's easier to see what's going on. The blue line is the measured position. The red line is the estimated position. The estimated position is actually cleaner, less noise than the measured position. So this is one reason that you might want to use the estimated position in the servo compensator rather than the actual one. And that just changes your matrix. Over here, right here, instead of doing C times the actual position, I would put it over here. C times the measured position goes into the servo. Doesn't really change anything, but it does work a little bit better because I no longer have the noisy measurement going into the servo. I have the filtered measurement, the blue line stuff from the Kalman filter. And again, you can kind of see that the estimated output is better. Take the standard deviation. Standard deviation of the measured output has standard deviation of 6 millimeters. The filtered output is 2 millimeters. That's a better measurement. So that's homework set number 11 for ECE 463.